Okay, so now we're going to talk a little bit about rotational kinematics. And the beauty of this is you don't really need to learn anything more. Okay, so rotational kinematics is exactly analogous to kinematics, linear kinematics, translational kinematics in one dimension, say along the x-axis. So if you understand, position, velocity, acceleration along the x-axis and the relationship between those quantities, then you will immediately understand by analogy rotational kinematics. So let me sort of illustrate that with an example. So suppose we take the x-axis to be vertical. We'll see why in a second. Okay, and we'll suppose that this is x equals 0, and we'll suppose that we have an object which starts here at some position x initial, and it has some initial velocity, say small, positive, so this is vx initial, and then under that velocity and acceleration it comes to this point x final sometime later, and it has, say, a larger velocity, vx final, because there's been some acceleration in the x direction. So this is vx final. And so what are the relationships between these quantities and the acceleration? So in the case that the very special case that the acceleration in the x direction is constant, okay, then we have a relationship between these quantities, and you'll all remember this formula. We have x final, the final position of the object, is equal to x initial, the initial position, plus vx initial, the initial velocity that it had at that point in time, times the time interval, plus 1/2 the constant acceleration in the x direction, times delta t squared. Okay, so that's an example of a kinematical formula in translational motion, just one-dimensional translational motion along the x-axis. Okay, now let's see how this translates by analogy to rotational kinematics. Okay, so I'm going to take this x-axis, and what I'm going to do is I'm going to curve it from this point into a circle. Okay, so here I go. I curve this into a circle. And what does this circle represent? Well, what it represents is as you move along that circle, it represents a point on a rotating rigid body. Okay, so we had our rigid body. I don't want to mess up this diagram too much, but we've got a rigid body. In fact, why don't I not mess it up? And let's just suppose that we have a rigid body like this, and it's rotating about its center of mass like this. And so we have a point P, which is on the rigid body, and it is moving around in a circle like this. And now it could be, it starts at some initial tangential displacement over here. So this is S initial. So instead of x initial, how many meters? 1, 2, 3 meters you started along this linear x-axis. It's 1, 2, 3 meters along this arc of a circle. Okay, that's the initial tangential position. And then the final tangential position is over here. The point P is moved from here over to here. Okay, so let's take this x final. Let's bend this x-axis over. Let's suppose that x final becomes s final. The final tangential position, so instead of it started at 1, 2, 3 meters, 4, 5, 6, 7, 8, 9, 10 meters is its final tangential position. Okay. And then it started, instead of with an initial velocity in the x direction, it started with an initial velocity in the tangential direction. So that's v tangential initial. So it's moving at a certain number of meters per second in a tangential direction, tangential to the circle. Okay, and so r here is the radial distance, the perpendicular radial distance from the axis of rotation of the rigid body. This is the axis of rotation here of the rigid body, the perpendicular distance from that axis of rotation to the initial point P on our rigid body. Okay? And so it starts with some initial tangential velocity, v tangential initial, and then it's undergoing some kind of an angular acceleration. It's rotating faster and faster and faster. Okay, and so the tangential velocity, when it gets to this point, will be larger. V tangential final is analogous to Vx final, which is larger, because there's been some angular or tangential acceleration in the counterclockwise or positive direction. Okay, so then we can just proceed exactly by analogy. So the relationships between position, velocity, and acceleration in one-dimensional linear motion are exactly analogous to the relations between tangential position, tangential velocity, and tangential acceleration in the case of rotational kinematics. Okay, so x final is measured in meters, so is s final. So this is by direct analogy, S final is equal to X initial is measured in meters, so is S initial, plus Vx initial is measured in meters per second, so is V tangential initial. So this is V tangential initial times delta t plus 1/2 in the case where the tangential acceleration is constant. Just like the linear acceleration x is constant, we will have a tangential acceleration, constant tangential acceleration, times delta t squared. Okay, so if you know any formula, this applies to any formula in one-dimensional translational kinematics, you can always convert to a corresponding formula in rotational kinematics dealing with tangential quantities, meters to meters, meters per second to meters per second, meters per second squared to meters per second squared. Okay, so instead of motion along an x-axis, we have motion around a circle. Okay. And then, but remember that whenever you're dealing with circular motion, there are tangential quantities and there are also angular quantities. So there's tangential positions and there's angular positions. There's tangential velocities and angular velocities. There's tangential accelerations and angular accelerations. And remember the relationship between these things. Okay, so we have that the angular position, or sorry, the tangential position, let's put the R in a different position here. We have that the tangential position S, the arc length along the circle, is equal to the radial distance R from the axis of rotation times the angular position, theta. Okay, so S final becomes R times theta final. So if we take this entire equation and divide by R, then we have an S final divided by R. S divided by R is theta final. So we move from meters divided by R is meters divided by meters is dimensionless. This is in radians. So this is theta final. So this is the theta final. Theta final is equal to, take S initial, this initial S, this initial arc length along the circle, and divide by R. So S divided by R, it will be theta. In this case, theta initial. So the initial angle, theta initial. Theta initial here. This will be theta initial plus now V tangential. Remember that the tangential velocity is equal to R times the angular velocity. So if we take V tangential and divide by R, V tangential divided by R is omega. So in this case, it shifts from initial tangential velocity to initial angular velocity. So omega initial times time interval delta t plus 1/2. Take A tangential, so A tangential is equal to R times alpha. So so angular quantities are always tangential quantities are always R times angular quantities. Okay, and so if we take this tangential acceleration and divide by R, we will get the angular acceleration alpha. So this becomes alpha delta t squared. Okay, so just by proceeding by analogy, if you know any formula from one-dimensional kinematics, you can always convert that to a corresponding kinematical formula for tangential motion. Okay, so that's these sorts of quantities here. And then you can divide that equation by R, every term of that equation by R, and convert it to angular quantities, angular position, angular velocity, angular acceleration, that sort of thing. Okay, so really, really easy. So let me actually speak a little bit more generally, because this formula here is a very special case, valid for constant linear acceleration, and these two formulas are very special cases, valid for constant angular acceleration or tangential acceleration. Okay, but let's proceed more generally. So we know that in general, let's write this down, I guess, over here. Okay, so we know in general there's a relationship between omega and the angular position theta. So omega is d theta dt. It's the rate at which the angular position is changing, gives you the angular velocity. And so in order to come up with a general kinematical formula, like not one of these formulas that's just valid for constant acceleration, what we do is we just multiply both sides by dt and we integrate. Okay, and so what this leads to is a finite change in the angular position. So a finite angular displacement delta theta will equal omega average times the finite displacement delta t. This kinematical formula is completely general. It's true for constant or non-constant angular acceleration. So that's the relationship between the angular velocity and the angular position. There's also a relationship between the angular acceleration and the angular velocity. So the angular acceleration is the time rate of change of the angular velocity. Okay, and so what we do, like we did in the case of one-dimensional motion, we multiplied both sides of this equation by dt, and then we integrated both sides. So on the left-hand side, we just had the integral of d omega. Well, that's delta omega, the finite change in omega, omega final minus omega initial, over a finite interval of time delta t, and that's equal to alpha average, the average angular acceleration times the time delta t. Now, these two formulas are completely general, okay? And we can take these two formulas. These involve angular quantities. So angular position, angular velocity, angular acceleration, and we can convert those to tangential quantities. So all we do is we take both of these equations. We know that s is equal to r theta. So if we multiply on both sides of this equation by r, what we're going to get is the change in r theta. Well, the change in r theta is the change in s, delta s. And then we have an r times omega average. So this is r times omega average will be vt average. So this is the average tangential velocity times delta t. And similarly, we multiply this equation through by r. So this will become delta of r omega. Well, r omega is vt, so it's the change, the finite change in the tangential velocity, number of meters per second, change in that, is equal to r times alpha average. Well, r times alpha is tangential acceleration. You're converting from angular to tangential just by multiplying by r. So this r, alpha average, becomes the tangential acceleration average times delta t. Okay, so starting from the basic definitions of angular velocity and angular acceleration, you integrate, you obtain these general kinematical formulas. There's only two kinematical formulas in one dimension, and here they are. Okay, and then you can multiply both these equations by r and get the general kinematical formulas in terms of tangential quantities. This is tangential quantities, this is angular quantities. So these equations are always true, whether the angular or tangential accelerations are constant or not. Okay, but now just as exactly as we did in one-dimensional motion, we can consider the very special case where alpha is equal to a constant. Okay, so if the angular acceleration is constant, so the rate at which the angular velocity is changing is constant, so the increase in the angular velocity every second is the same amount, okay, then in that case we have, just like by analogy with linear motion, kinematics in translational motion, we have that because alpha is constant, it means that the angular velocity is increasing or changing linearly with time. And so that means that omega average here, let's do this one first, omega average, so let me put it here. So, here's omega as a function of time. And so if alpha is constant, it means that omega is changing linearly with time. So, maybe this is, say, omega initial, maybe this is omega final. So omega initial is here at some time, and then t initial, here's t final, and here's omega final. And here's the time interval delta t. And so then the rate at which omega is changing is just this constant slope alpha. So then omega average is going to be, it started off with this omega initial, it ended up with this omega final. The average is just halfway in between. And so that's just equal to 1/2 omega initial plus omega final. So So that's what omega average is in that general formula. And alpha average, of course, if the angular acceleration is constant, then the average angular acceleration is just that constant value of the angular acceleration. Okay, and so then you can, so if that's the case, then you can specialize these two formulas by plugging in these two expressions into there. And so then we get, for example, in the second equation there, delta omega, the change in the angular velocity, well, by definition, that's omega final minus omega initial. Okay, and so that's equal to alpha average, but that's just that constant alpha times delta t, times the time interval. And then delta theta, so delta theta, by definition, is the final theta minus the initial theta. Okay, so that's that, is equal to omega average. Well, omega average is 1/2 omega initial plus omega final, okay, times delta t. Okay, now we can stop there, but suppose that, that we know omega final, but we don't know omega initial. So suppose that this one is known. Okay, but we don't know omega initial. So what we'll do is we'll look at this previous equation. Well, there's an omega initial in there, and so we can express omega initial in terms of omega final and alpha times delta t. So we can write this as 1/2, so omega initial. Let's substitute in for omega initial. Omega initial, bringing it to the right hand, the negative omega initial to the right-hand side, will be omega final minus alpha delta t. Okay, and then we add to that plus omega final, a second omega final, and multiply that whole thing by delta t. Okay, and so in this case, we get 1/2 twice omega final, so that's just omega final times delta t, minus 1/2 alpha times delta t squared. Okay, and so this says delta theta, theta final minus theta initial, is omega final delta t minus 1/2 alpha delta t squared. Okay, and so this is exactly this equation over here, except we have, instead of thinking that we knew omega initial, we suppose we knew omega final. And so we just wrote this corresponding equation in terms of omega final instead of omega initial. So we have theta final is equal to, bringing the negative theta initial to the right-hand side, theta final is theta initial, this guy, plus omega final delta t, okay, minus 1/2 alpha delta t squared. Okay, so there's that sort of thing. So let's do a simple example here. So of where we could say apply a formula like this, where we say knew omega final, but we didn't know omega initial. Okay, so let me erase this here. And we'll do just a really, really simple example of rotational kinematics. So we're going to imagine just a wheel, and that wheel is going to be rotating around, and it will be undergoing some angular acceleration, which is constant. Okay, so we're going to give some initial things that we know, and we're going to try to figure out some, or we're going to give some things that we know, and we're going to try to figure out some other things. Okay, so the example looks like this. We say, suppose that we have a rigid body, say a really simple rigid body is a wheel. Okay, and that wheel is being rotated, say not about this axis or about that axis, but about an axis that's perpendicular to the plane of the page through the center of the wheel. Okay, so it's rotating around like this. And suppose that we are given the following information. So we're saying during a time delta t, which we know, during a time delta t, this wheel rotates n times around, like 11 times around or something like that. So during time delta t, we have wheel rotates n times around. Okay, and what we're given is we observe, oh, it has a certain final angular velocity with a known or measured omega final. So the things we're given are the time interval over which these changes are happening. We're given the fact that the wheel rotates n times around during that time interval, and we know the final angular velocity of the wheel, how many radians per second it's spinning around at. And what we're interested in is, so determine, for example, we might be interested in what is the angular acceleration. What is this constant angular acceleration? We're going to assume that it's constant. Determine the constant angular acceleration alpha. And maybe we would be interested in what is the initial angular velocity of that wheel. Okay, so in this particular case, a formula like this would be very helpful. Okay, so let's write down this formula. So delta theta, so delta theta is the number of, so the wheel rotates around n times, say 11 times. Each time it rotates around, is the angular displacement is 2 pi. So it's 2 pi times 11, so it's n times 2 pi. So delta theta is n times 2 pi. That is the angular displacement of any point on that wheel, okay, during that time interval delta t. So that's what delta theta is. And then that's supposed to equal omega final times delta t. Okay, so we know omega final and we know delta t. Subtract 1/2 this constant unknown angular acceleration alpha times the known time interval squared. So what we really want to figure out is that alpha. Well, now we have one equation in one unknown, and so we solve for that. So that tells us that the constant angular, we're assuming constant angular acceleration. So assume alpha is constant. And what is its value? Well, we just solve this equation. Okay, and so what we get is it's equal to, bringing this to the left-hand side, we have an omega final times delta t minus 2 pi n and 2 pi divided by 1/2 delta t squared. Okay, so we have something that looks like that. And now let's clean this up, this result up a little bit. Let's get the half out of the denominator and write it as a 2 in the numerator and have only 1 delta t down here. Okay, and so if we factor out a 2 divided by delta t, we're going to have, we have a delta t divided by a delta t, so we'll have an omega final. Okay, subtract 2 pi n divided by delta t. Okay, so it looks something like that. So that's what the angular acceleration is. And so if omega final is, say, really large compared to the number of times it's rotated around, then that constant angular acceleration is positive. If omega final is, or if it took a lot of turns to come up to that omega final, then the alpha is negative. The constant alpha is negative. Okay, so we just plug in whatever numbers we're given to figure out what alpha is. So we're done with that. Now we want to figure out what's omega initial. What was the initial angular velocity? Okay, and so we can just look at, say, this equation over here. So omega final minus omega initial, the change in omega is just alpha times delta t. We know alpha, we know delta t, we know omega final, so we can figure out omega initial. Okay, so we write down omega initial. Omega initial, taking that to the right-hand side, is omega final minus alpha delta t. Okay, and so that's omega final minus alpha times delta t. Well, this is alpha. Multiply by delta t, it kills that one. So we have minus 2 omega final plus 2 times 2 is 4 pi n over delta t. And so we have an omega final minus 2 omega final is negative omega final. And we have a positive 4 pi n divided by delta t. Okay, and so then we're done. We figured out alpha, the constant angular acceleration, and we figured out omega initial. And then we can just double check. So it's always good to double check things, find ways to double check things. So we know we're given omega final, and we just figured out what omega initial is. So then omega average. So omega average is 1/2 the initial plus the final. So that's equal to 1/2 omega initial plus omega final. So let's see, 1/2 omega initial. So 1/2 of this is 2 pi n over delta t minus 1/2 omega final. And then we have a plus 1/2 omega final. Oh, right, sorry, of course, this cancels out. Okay, great. So then we have omega average is 2 pi n divided by delta t, and 2 pi n is just delta theta. That's just the angular displacement over, n rotations there, 2 pi n divided by delta t. And that is omega average. Omega average is, if we just look back here, omega average is just the total delta theta divided by the total time. Okay, and so we're good. My sign threw me for a second. Yeah, so very good. So, so rotational kinematics, the basic idea is that from the basic definitions of angular velocity and angular accelerations, we get these two kinematical formulas, which are always true. This is for angular quantities. If we want to convert those to tangential quantities, we just multiply both of these equations by r, and we get the corresponding tangential quantities. Okay, these are always true. In the case that the angular acceleration alpha is constant, then just like in linear motion, the average velocity is 1/2 initial plus final. Here, the average angular velocity is 1/2 initial plus final angular velocity, and the angular acceleration average is just the constant angular acceleration. And then we can plug these two relationships into these formulas and generate all kinds of other formulas, whatever we need for our given problem. So in this given problem, we were given the time interval. We were given basically delta theta, okay, going around n rotations. We were given omega final, but we didn't know omega initial or alpha. So, so then we used this equation, and we cranked it out, and we could figure out the two unknowns, alpha and omega initial. And then we could just double check the result. Okay, so the basic point is that rotational kinematics is exactly analogous to translational kinematics in one dimension. And so once you know translational kinematics, you know rotational kinematics.